Hello everyone, welcome to today's workshop. My name is Fuad, and today we'll be learning about the basics of artificial neural networks. In today's workshop, we'll be building a high-level ANN that will train on a churn model dataset of imaginary customers at an imaginary bank. We'll be using two very powerful tools for machine learning and deep learning, namely TensorFlow and Google Colab. Before we move on, let me tell you more about the assembly and what we do here. The assembly is a smart lab based out of In5, and we have over 300 free workshops available since December 2014. We have three categories for our workshops. Firstly, the hack workshops are for embedded systems, IoTs, and hardware. You can think of things like Raspberry Pis and Arduinos. The code workshops are for software projects, so we can learn how to use certain APIs and frameworks to create certain apps. And finally, today's focus, data science, where we'll be looking at machine learning or deep learning techniques to create AIs. Our targeted audiences are namely students, professionals, and entrepreneurs, but our workshops are available for everyone who's interested in these fields. Our workshops focus on smart technologies and practical applications. For more information, feel free to visit our forum on members.theassembly.ae. Also, you can find us on social media at MakeSmartThings on Facebook, Twitter, and Instagram, and The Assembly on YouTube. Finally, let's begin with the workshop. Let's first get into neural networks. Neural networks are a series of interconnected neurons in a structure of layers. These neurons assign mathematical weights and biases to the input signals they receive from other neurons, and they pass their information forward into another layer, assuming there is another layer to pass information to. There are three types of layers: input layers, hidden layers, and output layers. The input layers simply consist of the neurons that contain inputs or are features. Likewise, the output layer consists of neurons, or even one neuron, that contains the probability of the output designated to that neuron. The probability indicates the likelihood of the label we're trying to predict. More on features and labels in another slide. Finally, the hidden layer is where the magic happens. A neural network can have many hidden layers and hundreds or even thousands of neurons. Each neuron more and more accurate every epoch, to a certain extent. Now let's look at some of these functions. Firstly, we have the activation functions. These functions tell neurons what to do with their computations. For this workshop, we'll be looking at two activation functions, namely the ReLU, or rectified linear unit, and the sigmoid function. There are many different activation functions, each with their own uses, but for the scope of this workshop, ReLU and sigmoid will do just fine. Firstly, on the left, the graph shows the ReLU function. ReLU simply returns the maximum value between 0 and the output, which is z in this case. This means that all values of z are pushed to 0 if it's negative, and all positive values are unchanged. And sigmoid, on the other hand, is a little more complicated but fairly easy to understand. Sigmoid function amplifies the outputs to a closer value to 0 or 1, based on whether or not you have a positive value. So positive values will be amplified to 1, whereas negative values will be pushed much closer to 0. Generally speaking, values over 0.5 are considered 1s, and values under 0.5 are considered 0s. Now let's briefly look at loss functions and optimizers. Loss functions are functions that will help calculate the errors in our output. When training in supervised learning, we know the correct output our neural network should get. Our loss function will compare the correct output with our calculated output and will return a loss value. There are many different loss functions that calculate loss in different ways, but for this workshop, the binary cross-entropy function will do, as we're only predicting whether or not a customer will leave a bank, so essentially a 0 or a 1. Optimizers, on the other hand, are what adjust the weights and biases in order to minimize the loss that we calculate in the loss function. For this workshop, we'll be looking at the Adam optimizer, which is commonly found everywhere in the data science field. And using these techniques, our neural network is essentially undergoing backpropagation. Backpropagation essentially means calculating an output and going back to change the weights and biases in order to be more accurate and minimize our loss. Now here's a bonus slide before we move on. Here's a little extra resource that will help us visualize the neural network we've been learning about. It's a little web app created by Ryerson University that will read handwritten digits and activate the node corresponding to that number. For example, if you draw the number 2, the neural network will return the digital number 2. Okay, so here's a little web app created by Ryerson University that will ask you to draw a number here, and it will predict using the deep learning techniques what your number actually is. So for example, if I draw 2 here, it's going to go through all these different layers, and finally it's going to predict a number 2, which also tells you here. Its first guess is 2, and just in case that could be wrong, which it isn't at this point, its second guess was 1. Now let's see how this works. Now, the first 4 hidden layers you see here are actually convolutional layers, which we're not looking at. That's out of the scope for this workshop, so let me just hide them for now. And let's look at actually these 2 layers here. Now, each layer here takes information from the layer before it, and as you can see, it takes in a lot of information. Now, when the nodes, or rather the neurons, are actually light blue, that means these are activated, and a bit darker blue means they're a bit less activated, but they do have some sort of weight. Now, if you keep in mind, some of them are black, that means they found no features that they're interested in, so they will just remain deactivated. So again, every single neuron takes data from its previous hidden layer, and again, these get passed on to the next layer. Now, as you can see, in the next layer, it's taking information from everything in the previous layer. And a lot of the neurons are activated, but they're not that strong, except for a few here, and so on. And then finally, in your output layer, everything is essentially deactivated except for its predicted 2. Which is correct at this point, because all the weights that have been adjusted and pre-trained before are now telling it that based on all the information you're giving me, this is around, like, for example, 95 or even 99% sure that the number drawn here is a 2. Now we can actually try different numbers. So let's try 3. It's gonna, again, all these neurons will change because they each have a different weight and bias based on the inputs they're receiving. Again, the pre-processing that went on here is a bit too complicated rather for this workshop, but just know that this is similar to what we're going to do in the coding session. And again, notice again that a lot of these are also activated, but they're not that strong. Let's say they're not very strong signals. And once the output layer is reading everything from the layer before it, it realizes that, okay, this is actually most probably a 3. Finally, we can now see our data. The .csv file in the handout contains information of all the imaginary customers at an imaginary bank, such as their names, their age, their gender, their balance, and so on. Moreover, the last column tells us whether or not the customer has left the bank 6 months after this data has been taken. Now let's break down our data. Whenever we have data, we always need to look for our features and our labels. Features are the independent variables which are our inputs into the neural network, and they provide a description of an attribute. Labels are the dependent variables, namely our outputs of the neural network, and they're what we want our model to predict. Choosing effective features is one of the most important steps in data science. The entire field of feature engineering helps decide on which features we want our machine to learn from in order to reach our goals. Before we move on to choosing our features, let's look at some of the common data pre-processing methods that we'll be using here and in many other projects. Firstly, every deep learning model needs to undergo some sort of feature scaling. Feature scaling or normalization is essentially scaling down or adjusting all our values. For example, we can scale all our values from 0 to 1. Again, this is essential in every deep learning model. Secondly, we have the label encoding method. Label encoding is simply categorizing data as a 1 or a 0. For example, for our gender column in our data, we can actually label encode males to 1s and females to 0. Finally, we have one-hot encoding. One-hot encoding is a method of categorizing n types of data as a list or an array of n length. All the indices of the list will contain the number 0 except for 1. The index of the 1 in our list identifies our data. For example, in a list of 3 countries, France can be 1 hot encoded to 100, and Germany can be encoded to 010, and so on. So now we can get back to breaking down our data. To begin, we can easily identify our label or our output for this neural network. Since we only want our model to predict whether or not someone is going to leave a bank, our exited column will be our label. In this example, we have no other labels that we're trying to predict, which is why we also use the binary cross entropy function as we mentioned earlier. For our features, however, we need to be more careful. Some data may be useless for a machine to learn from, and good data is essential to building effective networks. So here's a question. Do you think that the rest of the columns are going to be good features? You can pause here to think about it, and we'll be going over this in the next slide. Now the answer is no. And to understand why, let's think about it intuitively. Let's take the first column, the row number. Would that give us any useful information about our customer? I mean, it doesn't mean anything to us, so why should it mean something to our machine? But be careful, sometimes using this logic, there are some features that we may believe makes no sense to us, but in fact have a very big effect on our labels. Our machines are able to find some correlations that we would never think of, which is why many people believe that AI is the future in almost every industry. So for our data set, we can safely disregard the first 3 columns, namely the row number, the customer ID, and the surname, as we believe that So for our dataset, we can safely disregard the row number, customer ID, and the surname columns, as we believe they will have no influence on our labels. That leaves us with 10 features, namely the credit score, geography, gender, age, tenure, balance, the number of product, whether or not the customer has a credit card, or if they are an active member, and their estimated salary. Now we're all set. Now we can start beginning coding our neural network. So now we'll be opening up our Google Notebook. And to begin, let's go to File, Open Notebook, Upload, choose File, and find the directory that you downloaded the notebook in, and upload the IPYNB extension file. And once this is done, it should open up the notebook. And here you'll have the notebook that we already wrote for you guys, and all we need to do is write the code in. So first thing, before we start, we'll first go to Runtime, change runtime type, and for hardware accelerator, we'll choose a GPU. This makes sure that our code runs on the cloud GPU given to us by Google. If you're not familiar with any notebook type of environment, you have things that are just text here and they have no effect on your code. And then you have these code cells where you can write code and then you can press run, and they will run in the order you run them in. So you can essentially compartmentalize your code and run them bits by bits instead of everything all together. So let's begin with the first step, which here is the data processing, and we want to import our libraries. So all we'll do is just type import NumPy as NP, import pandas as PD, and import TensorFlow as TF. And to see what version of TensorFlow we're using, we're just going to do TensorFlow _version _. And now after we've written our code, we just need to press run, and it will run all the code in this cell. It may take a second to initialize everything to connect to the cloud, but after this should be pretty quick. So now it's running, and we see that we're running TensorFlow version 2.4, which is the newest version. Now we need to import our dataset, but before that, we need to go click on this file icon, click on this upload icon, and find our churn modeling dataset, which is a .csv file. And then just press OK. In a few seconds, you'll see that your churn modeling dataset, or any dataset really, is uploaded here. So now we have it as churn_modeling.csv. Now, if you're not familiar with pandas, we're going to be using this to actually store the entire dataset into a variable called dataset. So we do that by first creating a dataset, and we'll set this equal to pd dot. And if you guys want to see what functions are available, just press Control space. And then we'll be looking at the read underscore CSV function. And then we'll just pass in the name of the dataset, which is churnmodeling.csv. And then finally, we can just print the dataset to see what it looks like. So as you can see here, our .csv files has all these information. And there are some cropped out because it's a very big file. You have around 13 or 14 different columns, which is fine. So now let's just create a new code cell just by moving your mouse down here and pressing code, and you'll get a new cell. Now what we want to do, we want to separate our features and our labels, and we want to get rid of the first 3 rows, right? So for our features, we'll name them X, and we'll make them equal to dataset dot. Now in pandas, you don't get arrays, you get things called data frames. Now we want this to be a list, so we'll be using the ilock, and then just like an array, we want to pass all the rows and columns that we want. Now we want every single row, so we'll just put a colon and then a comma. And then for the columns, we don't want the first 3 columns, and we don't want the last column because that's our label and it's not our feature. So what we'll do is, so this is index 0, 1, 2, so we want index 3, and we're going to go all the way to -1. Now keep in mind, when you use a colon, you don't count the last index that's in your brackets. And to return this as a list, we'll just do dot values. Same thing for our labels, but instead this time we'll use y is equal to dataset dot ilock. We want all the rows, but this time we only want the last column and nothing else. We'll just put a -1 dot values. And now we can see what these look like. So we'll print X and we'll print Y. So as you can see, we actually got rid of the first 3 columns in our features, which are these. And for our last column is just our exited column. So you can see 101 and it ends with a 110. So now X is our features and Y are our labels. Okay. Now let's get to encoding the data. Using our data preprocessing tools, we will first encode the gender column to 1 and 0s. So essentially, once you run this cell, it's going to change your second column. And let's just print that out, just see what it looks like. Print X2. Once we run this code, you'll see that males will be encoded to 1 and females will be encoded to 0. It doesn't matter what gets encoded, as your artificial neural network will learn this anyway by itself. So we'll just run this code and we'll see what happens to our gender column, right? So we get 0, 0, 0, and let's go back up here. And you can see that females, so this is index 0, 1, 2, and we encoded the second column. So 0 will be females, and then the end, you notice we got to 0, 1, 0. That's because we have female, male, female. So the male got encoded to 1. So we know that this cell is done. For one-hot encoding, we'll be one-hot encoding our geography column, which is the countries. And since we have 3 countries, we have an index, we have rather a list of size 3. So if we run this code, firstly, if you ever want to change, if you're using this for another data set, you can change which column you want to one-hot encode just by changing this number here. But for us, since this is index 0 and index 1 is our geography, we only want to one-hot encode our geography column. And keep in mind, when this happens, it's going to shift your geography column to the first 3 columns, with the first 3 columns being your one-hot encoded. You'll see what this looks like if I just print X. Let's run the cell. So as you can see, we get 100 for France, and then Spain would be 001, and then Germany would be 010. And that means your one-hot encoding is done. And keep in mind now the index isn't 1 anymore, but it's going to be 0, 1, 2, and index 3 would be your credit score. Finally, we want to split our data into training sets and test sets. This test set size over here, which is equal to 0.2, will take 20% of your data set and make that into a test set, and split it again into X train and X test, Y train and Y test. Your Y, again, are your labels, and your X's are your features. So let's just run the cell, and we'll be using X xtrain, xtest, ytrain, and ytest from now on. And again, like we said, feature scaling is a must in deep learning. Now, what this does, a standard scaler is essentially a normalization. So it's going to find the mean and it's going to find the standard deviation. It's going to scale everything into a normal distribution curve. So again, we'll just run this, and in fact, if we even print xtrain, for example, you can see what happens to the code, right? So everything is normalized. Again, you don't need to do this by hand. There are a lot of code out there that does this for you. As long as you know how to use them, you should be okay. So now we're done with the data pre-processing, and now we can actually start building the artificial neural network. Now, as we said, everything needs to move in a sequence. So you're moving from an input layer into a hidden layer into an output layer. Essentially, you can think of this sequentially, which is why the class is called sequential. So let's just begin by creating a class called sequential, which is available in the TensorFlow library. So we'll store it in something called ANN, and we'll make it equal to tf.keras is the high-level TensorFlow library. And we'll go to, you can actually press Control Space, see what you're looking for. We want to look for models, and we'll want to find the sequential class. And once you're done, ANN will be a sequential class from the TensorFlow keras library. Okay. And now we want to add our hidden layers. Now, hidden layers are actually, well, in this case, they will be part of the dense class, as we want everything to be interconnected, and they will all be in one layer. So what you can do is, by adding a layer to our artificial neural network, we'll just use the ANN.add function. Once we do that and we press Control Space, we can actually see what we're looking for. It's saying it needs a layer. So we'll look for tf.keras.layers. And for this one, again, we'll be using the dense, and you can see what dense is, or rather what it's looking for. Here it tells you that dense is just your regularly densely connected neural network layer. It's very basic, and it's what we'll be using today. Now, the first parameter up here, you can see our units, which asks us how many units we want, how many neurons rather we want to have in our neural network. So for this exercise, let's just try 32. And then also it will ask you for an activation function, and we'll be using activations equal to relu. And everything else can be standard, and that's all we need to do for here. And let's just run this to make sure we don't have any errors. And it runs pretty quickly. Then again, let's just add another hidden layer. So the first hidden layer will basically connect to every single node in the second hidden layer. So let's just do again what we did here. We don't need to write the code again, we'll just copy paste that. But here, instead of 32 neurons, again, you can use 16. You can play around with the units, you can play around with the activation functions if you want. You can see which one's better, you might even get a better result than I do. Okay, and finally, let's look at the output layer. So again, to add a layer, we'll do ann.add, we'll look at tf.keras layers dense. And for our output layer, since we're only predicting whether a customer is staying or not, we will only have one unit, right? So if it's a 0, that means the customer is staying, and if it's a 1, that means the customer has left the bank. And finally, we'll need to add an activation function, and for this one, we'll be using sigmoid to help push it between 0 and 1. We don't really care for bigger values than 1, and we don't have negative probabilities, so sigmoid will do perfectly here. And again, let's just run these two cells. So later on, what you can experiment is adding more layers, or even trying with one layer and changing the number of nodes and what type of activation you use. You can get different answers, but again, for now, these will do. So now we want to actually compile and put everything together, which we have the function for, which is just ann.compile. And we can see all the parameters at once. Firstly, it wants an optimizer. And if you remember from the slides, we said we'll be using the Adam optimizer, which works in most cases, so you should be fine using this everywhere. And for the loss, we'll be using binary underscore cross entropy. Now there are a lot of loss functions rather, but for this case, since we're only predicting if they're leaving or staying, binary cross entropy will do fine. And finally, metrics is just the things you want it to print out while it's training. So I want to look at the accuracy and how that's changing while my neural network is training. So we'll just compile this and hopefully we get no errors. And perfect, it's compiled. So now we want to train the neural network on our data. So what we'll do is we'll just use ANN dot, and we'll use our fit function. Now, if we look at all the parameters it needs, firstly, you want your X and Y, and keep in mind, we'll make X is equal to X train because we're training our set, and Y is equal to Y train. Okay. And now for batch size and your epochs, you can really put any values you like. You can test out different values, but you have to be careful of overfitting or underfitting. Again, this is more advanced and you can look more into this later. But for this workshop, we'll just be trying a batch size of 32 and we'll be going for 100 epochs. Epochs are essentially how many iterations you want to go through. And let's just run this. And once you run this, you can actually see your neural network learning. So if you look here in the beginning, your accuracy starts at around 75%, but then your biases and your weights will actually change and you'll become more and more accurate every epoch. Now this may take a minute or so to train, so we'll let this happen and we'll see you once it's done. Okay, and our neural network has finished training, and as you can see in the last epoch, we actually reached an accuracy of 88%, which will do actually really well in the things we want to test today. So again, if you want to see what your neural network looked like, you could just run this ANN.summary and you'll get everything here. Now let's actually test our ANN and see if it can actually predict whether or not a customer will leave. So assume a customer with these details. They live in Germany, they have a gender score of 750, they are male, they're 30 years old, They are 30 years old, they've been at the bank for 4 years, they have 150,000 euros in their bank account, they have 2 products from the bank, they have a credit card, but they are not an active member, and we estimate their salary to be somewhere around 90,000 euros. These are all given. So now we actually want to ask ourselves, is this customer going to stay or is he going to leave the bank? Now again, note the following: when we encoded our data, this male column was actually encoded to 1, whereas females were 0. And then our geography was actually 1 hot encoded into 001 or 010, but since our customer is in Germany, we'll be using 010. Now to do that, we'll be actually running a predict function that's available through TensorFlow, and we'll be using a transform, and I'll explain why in a second. But essentially what you add are this first row is the geography, which is 1 hot encoded, so we just put 010, and then you have your credit score, and you can just fill in the information here. 1 actually shows you that he's a male, 30 is 30 indicates that their age, and so on. And we said, since we use the sigmoid function in our output, if anything's over 0.5, that means they're leaving, or it gets a quality of 1 or something really close to 1. So if actually we run this code, we'll see that the customer is likely to stay for the next 6 months, right? And we'll see that the prediction is actually false because it's actually less than 0.5. Now, keep in mind that the predict function takes a 2D array and not a 2D list. So that's why we just put the double brackets just to put it in properly. Finally, let's try it with another customer that's from France with a credit score of 608. They are female, 42 years old, and so on. If we again similarly put all their details here and we run this prediction, we'll see that the customer will actually leave the bank in the next 6 months, as opposed to this person who we predicted would stay in the bank. Now here I just predicted the output layer, so it's 99.8% sure that this customer would leave the bank in the next 6 months. Thank you so much for watching. We hope you enjoyed this workshop and we hope you learned something new about artificial neural networks. If you're interested in more of our workshops and want to be updated, consider subscribing to our YouTube channel and clicking on the bell icon for notifications. Follow us on social media at Make Smart Things on Facebook, Twitter, and Instagram. Stay safe and continue learning.